Hi, my name is Keith Schilling. I'm the State Geologist of Iowa and the Director of the Iowa Geological Survey at the University of Iowa. We're standing today at one of my favorite places in Iowa, which is the Neil Smith National Wildlife Refuge outside of Prairie City, Iowa. This is a location that the Fish and Wildlife Service has been working to convert former row crop land of corn and soybeans back into native prairie. And this is a really good place to start a discussion about why streams are the way they are. And we really can't talk about the formation and the behavior and characteristics of streams without thinking about the watershed that drains into them. This is a great location to stop and take a look at what the landscape used to look like pre-settlement versus what it looks like today in many areas of Iowa. If you pan over to the left here, this is a prairie restoration that the Fish and Wildlife Service has been working on for 15 or 20 years. And you can kind of see that it's dominated by tall grasses, and if we're out here at a different time, you'd see beautiful flowers and forbs. And this is a landscape that Iowa used to consist of, okay? This is tall grass prairie, had been around for thousands of years. And this is a landscape where precipitation falls on this landscape. Most of the precipitation infiltrates and is taken up by the plants and evapotranspired back into the atmosphere. So a landscape with native prairie is an infiltration-based landscape. You can kind of see the roughness of this land. We're not going to get a lot of runoff. Most everything soaks in like a sponge. On my right here is what the landscape was converted to. In the late 1800s through today, much of this land that wasn't prairie has been converted to row crop farmland for corn and soybean production. And what this landscape is, you can kind of tell at this time, we're in the fall, it's all been harvested, and what we see is a landscape that largely consists of bare ground with some residue on there. This is a ground that is not actively, we don't have plants and vegetation actively taking up that water. This is what it's going to look like until about June next year when the crops start to emerge. Rainfall, for the same amount of rainfall falling over here on this row crop land, a lot of it will run off. And when it runs off, it gets quickly routed to the stream. We have a lot of stream flow and discharge and flashiness behavior of the streams. So what we see is a landscape that was converted from an infiltration-based landscape to a runoff-based landscape. And in here, with most of that water running off or soaking up into the ground here with no transpiration by the vegetation, we see the hydrology completely different with these two landscapes. So this is a great location to talk about what happens when we convert a landscape from native prairie to row crop. You know, we've completely changed the water balance. You know, ET is greater in prairie than it is in row crop lands, and consequently we have less discharge and less runoff over here in prairie than we do with the row crop land cover. So because of that, we see our streams showing the behavior of that and having more water discharge in the stream and more water per unit area as this conversion has occurred. So when this discharge reaches the stream and we get a lot of runoff, and one thing to keep in mind is that today, through the efforts of the NRCS and the USDA, we are a lot better as a community of agricultural producers about keeping water on the landscape. You can see that we have residue here that is preventing some of that runoff from occurring. But historically, before some of these conservation programs developed, this was largely just fall tilled and bare ground. Raindrops hitting that are not really being taken up by the vegetation, and there's not a whole lot to prevent that runoff from occurring. When that water gets into the stream, it reaches there quickly, okay? Imagine an entire basin with slopes having water from this field getting into that stream, it's going to reach there quickly, and consequently the stream flow is going to rise really rapidly in that stream, and because of that rapid rise of stream flow with a lot of discharge coming in, we see a lot of consequences because of that. We see a lot of stream bank erosion, we see a lot of down cutting, and we see streams incising into their floodplain. So we're at a different location in the Walnut Creek watershed, the same watershed that contains the Neil Smith Refuge. We're up in the headwater area. The headwaters are essentially where streams originate. And in this location, and throughout much of Iowa, streams originate from subsurface drainage, tile drainage. And this is the location where stream flows just starts. It starts at the end of a pipe, flows underneath the road, and now we have a channel that migrates through the watershed. Tile drainage is done in Iowa in a couple different ways, but it's done mainly to improve the crop performance. Okay, corn and soybeans don't like to have their roots in water. We get some rainfall that can be poorly timed for when the crops need it, and so farmers and producers will put tile, subsurface perforated pipe, in the ground at about 4 feet down to drain this excess water and soil moisture. Many farmers and producers will install a network of subsurface drainage pipes throughout Iowa to drain the excess water and soil moisture to allow the crops to grow more effectively. These are typically 4-inch, 6-inch, they used to be clay, now they're black plastic perforated pipes that are put in low areas or in patterns across poorly drained fields to drain this excess water. In southern Iowa, in this landscape, the landscape tends to be more rolling, so a lot of the tiles are put in following the waterways or following the low areas in the landscape to drain that water off. There's a location right here beside us where the tiles are actually flowing. Even though it's November and it hasn't rained in quite a while, there's still some water seeping out of the tile. These low areas are drained mainly so these tractors can cross those and not get stuck, and also to prevent gullies from migrating up the watershed in these low areas. Where this tile is discharging right here, you're going to see that there's a grade stabilization structure put in there to support the tile network and also to prevent the gullies from migrating up the sides of the hill. You can see that there has been on both of these waterways gully formation because of the excess water from this runoff-based landscape. So here, as opposed to our location contrasting with the prairie, here's what we get a chance to see: this rolling countryside and row crop land cover on this rolling countryside. You see from the slopes behind me that raindrops falling on this landscape, freshly tilled with this ammonia fertilizer application, can really generate some runoff and some pollutant loads in our streams. These tiles that we talked about are the main source of nitrate nitrogen to our streams. In other locations in north central Iowa, these tiles are also the main source of the water in the streams. We did some work in the Boone River watershed and showed that these tiles can account for as much as 60% of the water flow in the Boone River can come from subsurface drainage tiles. It's really hard to underestimate the impact on the hydrology and the water quality from this subsurface tile network. These tiles, because they contribute flow to the streams, also contribute to the status of our streams in terms of the excess water delivered from these tiles, in addition to the runoff, is causing some of the erosion problems that we see in our streams. So these tiles, while they improve the agricultural productivity, have a huge effect on both the water quality and the water quantity in our streams. So we've moved locations, and now we're seeing the consequences of how we've changed this watershed from prairie to row crop with tile drainage and excess runoff. We're within the channel now of Walnut Creek, which is the third order channel the stream migrating through the Neil Smith Refuge. Early settler accounts mapped this area, and at that time they described Walnut Creek as being about 6 feet wide and something you could jump over. In fact, you could take your wagon across it and nobody would think anything of it. Today, you can see the channel is probably 50, 60 feet wide from bank to bank, and now it's been cut down or incised into its floodplain on the order of 10 to 12 feet. So this is the consequence of throwing or having a lot of extra water, high energy water delivered to the channel. Now, when it rains, instead of this normal system where the water would go up in the stream channel and then the water would dissipate into a floodplain, usually that would occur once every 1.5 to 2 years. Now, any flood flow is contained within the channel itself. It's only the most remarkable flows that have occurred maybe 2 or 3 times in the 20 years I've been out here studying that flow has ever reached the top of this bank and dissipated into the floodplain. So now all the energy of the water is contained within the channel, and we continually try, and this water continually is eroding the bed and the banks within the channel. You see evidence of this behind me. For example, this tree that used to be on the floodplain, now it's been eroded down. We see the roots exposed. This is the evidence, among other things, showing the extent of bank erosion going on here. What has slowed this, as opposed to the Luss Hills in western Iowa, which are more deeply incised than this, is that there's a bottom here to this stream. We have different layers of geology that make up the depositional environment of this floodplain. There's a bottom here that seems to be more resistive to erosion, preventing the stream from cutting down any further. So as these streams evolve over time, there's usually a quick incision where it cuts down to something that's going to prevent the bed erosion from occurring, and then it starts to widen. And what we're into this phase right now for this evolution of this stream channel is we're in the widening phase, and slowly we're going to widen this thing out far enough where the stream is going to start meandering within the newly formed channel. We see evidence of that in different locations, that this stream wants to meander, wants to migrate back and forth. And so we see some evidence up here, more evidence downstream, where even within the confines of this channel, we see the stream wanting to meander back and forth. So over time, this will recover. The time frame, though, it's something, probably beyond what we can comprehend. We've been doing restoration studies out here for 20 plus years, and we can see from our first stop that we can restore the hydrology a little bit in an upland. But as we go to this stream channel, this is the result of all the accumulated activities in the watershed scale causing this stream to be the situation that it is. This will not recover in anybody's lifetime, okay? This is going to take a long time to recover back to some normalcy as the watershed around it improves. So this is the last thing available that's going to recover within this restoration project for the watershed. So here we see evidence of what Walnut Creek, or what all streams want to do, which is they want to meander. They're like machines, okay? These streams are migrating down slope, they pick up sediment, and they erode sediment, okay? So what we see here is even within the confines of this incised channel, the stream is starting to meander. You see it hits an outside point in the channel, there's some deflection, it crosses over, and then we see a sinuous S-shaped curve around this other side of the bend. Okay, this is what the streams want to do, is they want to meander back and forth in their floodplain. So as we look at the stream elevation, we're less than an inch deep here. By the time we go on the outside bend here, we're up 4 or almost 5 inches deep. This is the deepest part of the channel. As this water is trying to meander, the deep part of the channel, called the thalweg, moves back and forth. Okay, it gets deeper on the cut bank side of the channel, it crosses over, and it cuts the other side of the bank out. In between, we oftentimes have these riffles, which are these fast-moving parts of the stream. Okay, so we have a pool, we have a riffle, and another pool. This is what streams want to do. This is the natural behavior of them. It's just unfortunate here in Walnut Creek is that we're seeing this in an incised channel that's 12 feet below its floodplain. But this is a natural feature of how streams want to move and migrate. The geology of this watershed is largely dominated by silt, which is a specific size particle typical of windblown loess. Okay, so we have this loess cap everywhere. That silt is largely the source of the sediment in the stream, so our bottom of the stream bed is largely composed of silt. Where we see some high energy pass over this substrate, then we kind of wash the silt and clay away, and we might be left with sand and gravel behind. And so in various riffle areas where we see some kind of flow, concentrated flow, we see a lot of the silt washed away, and we get more natural substrate of sands and gravels. Now, if you took a snapshot of one of these stream banks across here, what you're going to see is that we have a bottom of the stream bed, then we have a layer that used to be the top of the floodplain, okay, which is typically is a dark banded unit that you can recognize very easily if we had an exposed bank. The upper 4 to 6 feet here is all consisting of post-settlement alluvium. This is all the sediment that eroded from the landscape that filled the floodplain up, essentially. So we have a record of sediment deposition in this watershed over the last 100 and some years that record the deposition of early sediment erosion from the uplands in this floodplain. So the incision that we see here is both a combination of down cutting because of the high energy water, in addition to filling some of the bank height just because we have a lot of post-settlement deposition. Okay, so it's really we're accumulating this level of incision down to 10 or 12 feet, with half of it being the down cutting and half of it being essentially the deposition on top of it. So another consequence of this channel incision in the lower stream level than it was historically is what effect that's had on the riparian zone. In a normal stream situation, if you walk from an upland to the stream, things oftentimes get wetter because the stream is in closer contact to the ground surface. And these channel incision occurrences, what you've done is lowered the base level of the water. And what that has done is had a ripple effect out in the riparian zone. So now, if we walked up these banks and probably 30 or 40, 50 feet in, the banks are actually very dry. So instead of getting wetter as you go to the stream channel, we've dewatered this entire riparian zone and caused the banks to be dry, which is an interesting occurrence, but it really has an effect as a U.S. Fish and Wildlife Service try and restore a natural assemblage of vegetation along the stream banks. Well, you can't install wet meadow sedges next to the channel because it's just too dry. In fact, you could put an upland oak tree next to the channel, it would do very well because the banks are dry. So there's an implication here about how to even restore a situation like this when we've dewatered things so much that our hydrology is really out of whack. With this channel incision, that what we see, you might think, that's really unfortunate for Walnut Creek watershed that the channel looks like this and it bears this consequence of all the upland activities. Unfortunately, this isn't uncommon. This is really pretty much the state of most of our streams in Iowa, is that so many of them are incised into their floodplains. We have consequences of accelerated stream bed and bank erosion. Bank erosion in this watershed can account for half the sediment export in this basin is coming from stream bank erosion. So this is not natural, certainly not natural in terms of how this should have been behaving pre-settlement, but this is not uncommon. This is exactly what we see everywhere. In fact, more uncommon would be to see a natural stream that is in touch with its floodplain, that shows the natural features of cut banks and point bars, and is allowed to flood naturally into its floodplain. So here we've mapped the stream bank conditions up and down this watershed, and as much as 40% of the stream banks are eroding in this channel. In a natural floodplain environment, that might be about 20%. So we have at minimum twice as much eroding stream banks, and those are generating a lot of excessive sediment export from this basin. Sediment export, sediment is the main carrier for a nutrient of phosphorus. So when we talk about sediment export, we're also talking about phosphorus export downstream. That much of our phosphorus export here is coming from the stream banks and the stream bed as opposed to all the upland contributions. So if we're going to solve our nutrient problem for phosphorus or reduce sediment, we really need to think about addressing the hydrology in addition to any sort of application or any sort of land surface activities. Until we get the hydrology right, this was just going to naturally evolve over time and take a long time.